Assalamualaikum and good morning. Today I will teach you about the Routh-Hurwitz criterion, which is part of the chapter number 4. Okay, the Routh-Hurwitz criterion can be used to indicate that a characteristic polynomial or characteristic equation with negative or missing coefficient is unstable. The Routh-Hurwitz criterion is called a necessary and sufficient test of stability because a polynomial that satisfies the criterion is guaranteed to stable. The criterion can also tell us how many poles are in the right half plane or on the imaginary axis. Okay, so here the main idea of the Routh-Hurwitz criterion or RH criterion is to determine whether the system is stable or not. So I hope you still remember what is the characteristic of the stable system or unstable system. Okay, I just want to remind that if the system is stable, all the poles are on the left half plane. If the system is unstable, at least one pole on the right half plane. Okay, so in order to use this criterion, you need to first construct a Routh array. So given the transfer function as follows, we just focus on the characteristic equation. Okay, so here the denominator of this transfer function, we call it as a characteristic equation, and we will use it in construct the Routh array. Okay, consider the system shown in the figure above. Then the closed loop characteristic equation is given as follows. Alright, the Routh array is simply a rectangular matrix with one row for each power of s in the closed loop characteristic polynomial. Okay, next, this table shows the completed Routh array. So how to develop this one? First, we consider the characteristic equation here. And then we develop the first column. Okay, so the first column starts with s to the power of 4 because the biggest order of the characteristic equation is s to the power of 4. Then this is followed by s to the power of 3, s to the power of 2, s to the power of 1 until s to the power of 0. Okay, next we fill in the first row for this table, where the first row is actually the even term, start with a4, which is the multiplication with s to the power of 4. So the even term is a4, next is a2, then it is a0. Okay. Then the second row is the odd term. Okay, start with a3, then a1, then 0, because we just need to proceed. Even in the characteristic equation there is no more numbers, so you just put 0. Okay, so we just already complete these two rows, and basically these two rows we obtain the values from the characteristic equation. And after these two rows, okay, which is the third row and above, we need to use the calculation as follows. Okay, so let's see on how to find B1. Okay, so the calculation is that A2 you need to multiply with A3. Okay, then minus A4 multiply with A1, and then divide by A3. Okay, so I hope you know this sequence. Okay, let's look on the B2. Okay, so for B2, A0 multiply with A3 minus A4 multiplies with 0 and divide by A3. Okay, so please remember, divided by A3. Okay, next let's look on a B3. Okay, so B3, yeah, for B3 there is an virtual columns that you need to use, which is 0 multiplied with A3 minus A4 multiplied with 0. So actually there is another columns, the fifth column actually, which is all the zeros numbers, so I didn't put in this slide. Okay, so basically we get 0 values and divide by A3. Okay, so note that for the third row, s to the power of 2 row, all the denominator is A3, A3 and A3. Okay, A3, A3 and A3. So please remember that. All right, and you can proceed with the fourth row to find a C1, C2 and C3 using the same sequence, and also D1, D2 and D3. Okay, that will be completed Routh array. Alright, so how to use this Routh-Hurwitz criterion? Let's look on this definition. The number of root or poles of the characteristic polynomial that are in the right half plane is equal to the number of sign change in the first column of the Routh array. Okay, so this is the keyword. The number of poles on the right half plane equal to the number of sign change in the first column. Okay, first column. So we will see a detail later on. If there are no sign changes, then we can say the system is stable. Okay, next let's look on the exercise number 1. Test the stability of the closed loop system. Okay, so we have two figures here, A and B. So figure B is actually the simplified version of figures A after you find the complete transfer function C of S over R of S. So after that you will get the characteristic equation. Okay, we will focus on this characteristic equation to develop the Routh array. Okay, as the solution, since all the coefficients of the closed loop characteristic equation are present, then the system passes the Hurwitz test. So we must construct the Routh array in order to test the stability further. So looks at the characteristic equation, the biggest order is s to the power of 3. So we put it in the first column, start with s to the power of 3 until s0. Okay, and then we start fill the first row. So the first row start with 1, which is the multiplication of s to the power of 3, then 31, then 0. Okay, the second row is an even term. We start with 10, and next is 1030 and then 0. Okay, you can put more columns, then you just put 0. Alright, for the third row we start with the calculation. Okay, so yeah, you can use the previous calculation, or you can use this determinant calculation where you just put negative at the outside of this determinant. Alright, yeah, if you still can remember, first you need to multiply 31 with 1. Okay, I just use the previous term, previous sequence. 31 minus 2, 1 minus 1 minus 2, 103. Okay, so in this slide they simplify. Okay, 10 all divide by 10, so become 1 and also become 103. Okay, so 31 minus 1 minus 1 multiply with 103 divided by 1. Okay, and you can also do for the second row. third column, okay, here, and then the fourth column here. Alright, so after you finish all the calculation, you put all these values, okay. Alright, so let's say you already finished all this calculation, and we just, according to the Routh criterion, we just focus on this first column, okay. We just focus on this first column, okay. Alright, let's look on this sign change. First we have 1, okay, and the second row we also have 1 positive, and the third row we have a negative 72. So now it is negative. Before this it is 1 positive, then change to negative. So there is a sign change here, and it is a one-time sign change, okay. It is a one-time sign change from positive 1 to minus 72. And we go for the fourth row, the values we get is positive 103, okay. So this is another sign change from minus 72 to positive 103, okay. So in this first column there are 2 sign change, meaning that there are 2 poles on the right half plane, okay. So yeah, we repeat again. So actually the first column we have 1, 1, minus 72 and 103, okay. So it has 2 sign change from positive 1 to minus 72 and from minus 72 to 103. So this system is unstable with 2 poles in the right half plane. Okay, next there are 2 special cases for Routh criterion. The first one, a 0 may appear in the first column of the array, okay, and the second one is a complete row can become a 0. So if this happens, it is difficult to solve the Routh criterion, but there are solutions for that, okay. So let's see this example. Consider the control system with a closed loop transfer function here, okay. Then let's say you already developed this Routh array table. The problem here is that you will get 0, okay. You will get 0 here when you do the calculation. So how to solve this one? To solve this one is that you need to introduce this variable epsilon, okay. You need to introduce epsilon, okay. So after you, because if you still use 0, yeah, all the calculation after that will become 0. So this cannot be happen in the Routh criterion. To avoid that, you need to introduce a variable which is called epsilon, okay. So you just put this epsilon and then you continue all the calculation and you treat this epsilon as a numbers, okay. So proceed all the calculation until S0, alright. So the next step is, okay, considering just the sign change in column number 1, okay. So this is the first column, okay. You just focus on the first column. Alright, so now we focus on the epsilon. What happens if epsilon is positive? Okay, what happens if epsilon is positive? Yeah, you just, for simplification, you just can treat as a positive 1, right? So the first row, let's look on the first row of the first column, okay. This is 1, it is a positive. 2 is a positive, okay. Now epsilon is positive, okay, so here is a positive. Next, how about this one? 6, positive 1, yeah, you can just treat positive 1. 6 positive 1 is positive 6, minus 7 divided by positive 1, so you will get the value negative, right? Then same goes to this equation. You just substitute the positive 1 at the epsilon. So you get here is positive and 3 is a positive. Alright, so how many sign change? Yeah, you can see 2 sign change. So the system, we say that it is unstable. Okay, and it has 2 poles. Since 2 sign change, it has 2 poles on the right half plane. Besides that, you also can treat epsilon as a negative. Alright, the answer is same. Alright, you also will get a 2 sign change. Alright, we go for the second special case. Consider this a closed loop transfer function, and you just get this characteristic equation to develop the Routh table. So what happened is that when you calculate and develop this table, S1, okay, the row of S1 is all zeros. So this also cannot be happen in the Routh table where we cannot proceed. So how to solve this one? Okay, in order to solve this one, you need to develop an auxiliary equation. So this auxiliary equation is the equation above S1. Okay, above S1. So let's look carefully. A of S is minus 3 S squared. Okay, above S1 is S squared. Okay, so the multiplication term is minus 3. So minus 3 S squared plus 3. Okay, and this one is equals to 0. Then we perform the differentiation to A of S. Okay, you just differentiate to S, you will get minus 6S. Okay, so if you see this minus 6S, the order is 1. So refer to S to the power of 1, meaning that okay, this minus 6 can be filled here. Okay, so now there is no more rows with all zeros. Then you can solve this Routh array table. And after you solve this one, you will get it has 2 sign changes. Okay, then we can say the system is unstable with 2 poles on the right half plane. Alright, that's all for the Routh-Hurwitz criterion lecture. Thank you very much.